So we're going to talk about Cython today. The reason why we're talking about Cython is because at the beginning of our previous session, I said something like, if you want to really speed up Python, you're using the wrong language, which I still stand by. But there's some intermediate things that you can do to significantly speed up Python execution without completely switching languages or spending a ton of time on it. And the primary method is that we'll talk about today is Cython, and then at the end I'll mention a couple of other things. So what is Cython? Here's Cython's documentation, and it will tell you that it's a programming language that is intended to write C extensions to Python, and that's really all it is, right? It's a quasi-domain specific language, but really it's all just about integrating Python and C. You have to be a little bit careful because there's actually two competing versions of Cython. There's the stable Cython, which is stuck at version 0.29.36. And then there's the quasi-developer Cython, but that's the one where all the activity is happening. And that's version 3.1.0 alpha 0. If you do a pip install, I believe that it will pull down this one, the 3 branch. If you get your Python packages from other places, you may get one or the other. I, on my machine, actually have the stable thing installed for various reasons, so I'm using the 0.29 version. And so I will only be talking about features that are for both branches, but there are features on the 3.0 branch that aren't available on the 0.28 branch. So if you're copying a tutorial from somewhere and stuff isn't working, it's likely that's because you have the wrong branch. You have the wrong development version installed in your machine. For the example that we will be using today, I thought I'd do something quasi-relevant. And so what we're going to be looking at is inversion of the Kepler time equation, because who doesn't like a good pseudo-deterministic transcendental equation inverse? Also, to keep things simple and to not bring in NumPy arrays into and not to complexify things, I'm just going to do this for the scalar case. Here is a reference solution to the Kepler time equation inverse, so the Kepler equation inverse. So we, given a floating point mean anomaly and a floating point eccentric anomaly, we wish to find the floating point eccentric anomaly, right? Such that m is equal to capital E minus lowercase e times the sine of capital E. And the way that we typically do this is via Newton-Raphson iteration. The only thing that could potentially make Newton-Raphson iteration more complicated is how you initialize things. I'm using a Taylor expansion-based initialization. There's many, many others, but this is my reference code, right? So it's about as simple as you can get this. You set up your initial conditions. Because this is based on Taylor expansion, you're either in the case where the first or the second term of the Taylor expansion dominates, and then you set your tolerance. It can be based on the precision of the data type. I've chosen 1e negative 15 because the precision of the double precision floating point data type at 2 pi is just below 10 to the negative 15. It's something like 8.8 times 10 to the negative 16. So 1e negative 15 is a good tolerance. I'm also going to cap the number of iterations. There's absolutely no reason why this should take more than 100 iterations. So we're going to abandon the loop if that happens. And then I initialize the counter for the number of iterations and the current error, which I arbitrarily initialize to 1. And then I have my while loop. While my error is greater than the tolerance and the number of iterations is less than the maximum allowable number of iterations, I will do the Newton-Raphson step, the derivative of the 0 function divided by the current value of the 0 function subtracted from the current iterant value. And I compute the error just by evaluating the difference between the Kepler equation and the original mean anomaly. Here we go. I'm just going to set up a test condition to test this. So I'm going to use a mean anomaly of 60 degrees and an eccentricity of 0.999, which is, a marginally difficult case. It should be something that every single algorithm is capable of handling of this type. So we are almost guaranteed that it converges, but it will probably take more than a few iterations to converge, which is kind of the point here. So I'm going to do the pure Python version, and then I'm going to use the built-in IPython magic function timeit to get some timing information. The fact that it's running for so long means that timeit is actually having to do many, many, many iterations to get a stable estimate, because the way it works is that it continues iterating until it has a stable standard deviation in times. Okay, there you go. And so right now, the core execution took 1.9 microseconds plus or minus 33 nanoseconds per loop, and it had to do 7 runs of 1,000,000 loops each. Now, this 1.9 microseconds is not the wall time. It's not the human experience time. It is the core execution time without the IO overheads. If I want to see what the nominal execution time looks like, I would use just the time magic function, and I would expect a number that is larger than 1.9 microseconds. And there you go. The wall time is 11 microseconds, right? Because that includes all of the overheads, whereas timeit is just focusing on the core loop and the standard deviations therein. And if I do this a couple of times, you'll see that I have a lot of variability, right? Well beyond the 33 nanosecond level of the timeit output. So these are just 2 different metrics, but together they tell us the full story of how long this takes to execute. So the number to keep in mind is that 1.9 microseconds. Also, please keep in mind all of the caveats about execution profiling that I said last time. The computer is doing other things, the CPU is being clocked up and down, there might be background things that are being executed at the same time during some of the tests and not others, and so all these numbers need to be taken with a grain of salt, right? But hopefully we will see some actual improvements. Okay, so Cython, how does it work? I'm going to take the exact same code, literally one-to-one. And I guess the one thing to point out is also I'm not using the NumPy sine and cosine. I'm using the standard library, Python standard library math sine and cosine. So that's just a small caveat. It really shouldn't change anything because they're basically the same. Okay, so you can see this is exactly identical. Right, and the only thing that I've done is instead of putting it into a .py file, I have now done it into a .pyx file. So I have the exact code in this pyx file, and I am now what Cython is going to do is it is going to translate that pyx file into C code or into Cython compatible C code, right? And then it's going to compile that C code into a binary specific to my system. That binary will then be something that I can access from Python. So that's the basic idea, is you write something that looks a lot like Python code with some potential additions on top, which are Cython specific. That gets translated into pure C, and the pure C gets compiled. It can also be translated into C++ if you want to take advantage of C++ stuff, but we're just going to be focusing on pure C. So the way that I implement that is I need a setup file. And so this is a very, very simple setup.py file. This kind of extension can also be implemented in larger projects when this just becomes a piece of a broader setup file, like you would write for a Python package. But here we're just going to be building the executable, so we need a very minimal thing. And so I am pulling from Cython this thing called Cythonize, which is the act of translating to C. And then I'm setting this up as an extension module. And so this will build, so by running the setup.py file, I will first translate via the Cythonize call, and then also build it, okay? You can see that I have multiple different things here. So I can have as many different files in the Cythonize call as I want, and it'll build a separate blob for each of them when I do it this way. I also have given it this optional annotate thing, which will produce an HTML output, which basically shows me how well I'm doing in terms of utilizing Cython functionality. And under compiler directives, I'm telling it that I'm using Python 3 strictly because I'm using the 0.29 branch. By default, it would default to Python 2 syntax, which none of us need. The way that this works is I will need to call the setup file. And I do that as usual. I will do Python setup.py, and then the directive that I'm telling it is to build the extensions. That's what buildx does. And I also want them to be built in the current directory instead of inside of a build tree. So that's what the in place does. Okay. So again, if you are using Cython as part of a larger project, you will have a more extensive setup file, and then you will just be using, you can use that setup with pip install and other things, and that will automatically make all this happen. And that's what we do with exosystems as an example. In any case, so I run this, it thinks for a while, and then it successfully created all 3 things. So I have a V1, V2, V3. So far, we've only looked at V1, and then we'll be looking at V2 and V3 next. But you can see it did the translation, and then it actually compiled. And if I look inside of this directory, you will see that I have these 3 SO files, which is what the binary blobs end up being on Mac OS and under Linux, and on Windows they will be. I'm actually not sure what extension they end up. It's a different extension, but I think they're a different kind of shared object under Windows. But they will be a system-specific binary that can then be called.
What's Darwin?
Darwin is the internal name for Mac OS. Darwin is what they call the BSD kernel that they hacked to become Mac OS.
Okay.
So internally, yeah, Mac OS is known as Darwin. Good catch.
Question. Does it, if you run the build again, will it overwrite those files, or if it finds it, will it not?
Yeah, it won't do anything. Good question. If I do this again, it does nothing because it's analogous to the make system. It's smart enough not to repeat its work.
Yeah.
However, if I change any of those files, it'll rebuild only the part that was changed. So it's also smart enough to pick up changes on disk. Okay, so I said that it generated this HTML, which you can see right here. So let's take a look at that. This is not a required thing, but a useful thing. And so the yellow lines basically say that those are places where you are going to have significant Python interaction. And that's where the slowdowns happen, right? Python code inherently slow, compiled C code inherently fast. So as you're working through Cythonizing a project, you can use this annotation as a guide to show you where you should be saving time, where you should be trying to do more. And so unsurprisingly, the pure Python import is a lot of Python. So you can see like this is all the stuff that it has to add to do this import. And then this method definition has to have Python interaction. This is a bit confusing because there's 2 different things that you can do inside of a Cython file. You can do define a normal Python def, or you can do a cdef, which is pure C interaction. However, if you want to call the method that you generate from a Python interpreter session or from another piece of Python code, the definition of that method has to be a pure Python def. So there's nothing I can do about this. I can't get rid of this Python wrapper bit. So I'm always going to be stuck with it if I want this code talking to Python code. Okay, so obviously nothing happening in the comment, and then quite a bit of Python interaction happening here. And you can see that there's actually different shades for different levels of Python interaction. So here I'm defining E, right? I haven't typed it, so the C there has to be a lot of additional guesswork and like accommodating the fact that this can be basically any type, and then inferring the type from the inputs, which are also not typed themselves, right? And then I'm going to do operations on this, and this requires a lot of overhead because again, we don't have any type guarantees, and so there has to be a lot of guesswork. You can see things like if unlikely, etc. So just a lot of garbage that we can get rid of just by typing things, which is our next step. And then, of course, everything that has to do with the iterants, everything that once again has to do with defining things that are not strongly typed, requires Python interaction. Okay, so we have basically done nothing, right? And we expect our speed up to be very mild, right? But let's check. So we've created this object. We can now go back to our Python session, our IPython session, and we will import this Cython v1. And so it imports exactly like a normal Python module, and then we're going to time it. There we go. Okay, so remember, before we were at 1.9 microseconds, now we're at 1.34 microseconds. So we've accomplished something, right? Because it's hard not to do better than vanilla Python, but we haven't done much. Okay, so now let's start attacking the individual things in this file. And so we are going to now create a second version. And so again, this will be a couple of very small changes. Okay, so I'm going to get rid of this for a second. I'm going to comment this out just to show something. So still leaving the pure Python imports of sine and cosine, but I'm now going to explicitly type the input variables. These are all double precision floating points, so they're doubles. I'm going to internally define this. So that's why I'm using cdef, right? Because Python doesn't care about typing, but C does. So internally, this is cdef double E, and I'm going to similarly type every single one of these variables. And so that should take care of a lot of the typing overhead, which can lead to marginal gains. So I changed this, which means that, oh, also, yes, my Vim doesn't understand Cython syntax, which is why it's showing me a syntax error, but it's not. This is Cython code instead of Python code. So I can actually run the build again, right? Because I changed something. And so now it should only recompile that v2, which is exactly what it does. Okay. And now I can open the HTML associated with this. And you can see that it actually, like, if you compare it, it's still basically complaining about the same lines, not quite as much, but there's still quite a few complaints. Okay. And so it's always going to complain about the pure Python import. It's always going to complain about the definition of the method because it has to interact with Python. But I've typed this, so why is it complaining here? Well, if you open this up, you will see that it's doing a zero division error check, right? Because C hates that and Python doesn't quite mind it, but we haven't told it what to do in that case, right? And similarly, same deal here, right? It's explicitly adding additional checks for zero division for things that will be floating point underruns. And then here again, right, same deal, just much more so. There's still lack of clarity in terms of what things are and what things are being done. So that has to do with the thing that I commented out. I can import, and I can actually have a C import because again, I'm only using this in the C part of the code, the Cython package, and I can add a decorator to my method, and I'm going to tell it that we don't care about division checks. So we can skip all that. So I save that, I recompile. Good. And now my expectation is that magically these lines are now okay because it has been told not to do any division checks. And so now there is no Python interaction. There is still Python interaction happening here because this is using the pure Python sine and cosine methods, right? Okay, so let's see if this helped at all, right? So same deal, we import the module and we time it and we wait for a while. Okay, and so we've gained 1/10 of a microsecond. Not nothing, but not a lot. What I want to do next is attack the Python imports. And I know that I can deal with these because the standard C library has a perfectly good sine and cosine method. So there's absolutely no reason why I should be using the Python versions. Okay, so that brings us to version 3.
And is it that it's slow when it's calling the Python sine and cosine, or it's slow when it's importing the sine and cosine?
Both. It's slow importing, it's slow calling, it's slow executing, right? Because those methods themselves are not being Cythonized. So you're having the binary send data out to another binary, right? And back and forth. And so, yes, so it's slow all around. Okay, so here's version 3. So exactly the same as version 2, except I have now gotten rid of the Python math sine and cosine imports and replaced them with this. Now, if I was using the version 3.0, there's actually new functionality in the 3.0 alpha that allows me to do these imports directly without having to define external methods. But this approach works for all the things. So I know that sitting in my standard system path in the standard C library, there's something called math.h, which is all the headers for all the standard library math functions. I know that within those, there's a sine function and a cosine function. And so I can define external functions from any header that is in my system path or in any path that I compile against. And so I define a sine and a cosine, both of them operate on a double input and give a double output. That's it. This is the only difference between, so if we compare this against version 2, that's it, right? This is the only difference and everything else is 100% exactly the same. Okay, so I've already compiled this, so I can go straight to here and I copy and paste this. And let's see what happens. So this is now version 3, timing version 3. And we're down to 281 nanoseconds. And so now we have finally gotten the appropriate speedups. Okay. So to get here, we had to make sure that everything was typed. If I just tried to use the C functions without first typing things, I wouldn't get the full speed up. We had to make sure that everything was typed. We had to toggle off all of the useless checks. And there's a bunch of useless checks that happen, especially when you're using arrays. There's balance checking, there's looping around, but using the negative indexing functionality in Python that doesn't exist in C. There's all sorts of checks that you need to toggle off, otherwise they will just cruft up your C code. And then finally, we use the C library math functions. And we went from almost 2 microseconds down to under 300 nanoseconds. So now we're finally actually getting some appreciable gains. Because if you think about scaling this up, it scales really well. So you will recall that I wrote the PYX files. And you can see that in the process of Cythonization, it created C files. So we can take a look at these C files, right, just to kind of see what's happening in there. So let's look at the version 3 one. And like so that this is generated by Cython, right? So this is the translation of the PYX file into C. And like, again, the code that this generates is not anything that anybody would write. But if you read it carefully, you will find actual like interesting constructs that you can then use in your own C code. So it's not a useless exercise to look at these things sometimes, but you have to like ignore, 95% of the cruft because it's just handling all these possible cases that we usually don't really worry about. And this just goes on and on. So that's that one PYX file that was like 30 lines is thousands and thousands of lines of equivalent C code. We have one other thing that we can look at. What if instead of doing this, we instead wrote our algorithm in pure C to begin with? I created a subdirectory just to keep things a little bit separate. And in the subdirectory, I have in Kepler Cython v4. Oh, sorry. Before that, I wrote my own C code. So this is C code that I wrote that is not generated by Cython. And it is just an exact line-to-line translation of the Python code that I started out with. So we can compare the two. So here's the original Python code. And you can see that essentially this is a line-by-line transcription of the Python code into C. And I am also using the C standard math libraries. The only modification that I made from this is that I'm using a pointer for the return, and the actual return from here is the number of iterations, and that is so that I can interrupt execution at the Python level if I wish to do so, right? So in C, unlike Python, which automatically packages multiple outputs as tuples, in C, you actually have to define a structure if you want to do multiple outputs. It is typically much easier to just have multiple outputs by reference, which is what is happening here. So this is a pointer that I expect to be dereferenced as it's passed in to get the value that is assigned internally here, which is what this line is doing. Everything else in this code is 100% one-to-one. Oh, and I'm using the CMath FABs instead of the Cython built-in apps.
And you have, instead of squaring your centric anomaly, you're multiplying it by itself.
Correct. In Python, this operation has no perceivable difference. Yeah, has no like perceivable execution difference, although it might very slightly. In C, weirdly, calling POW2 is way slower than just multiplying something by itself, which is a quirk of the standard C library that I've never quite understood. So how do I get this pure C to talk to Python? Well, I use the magic of Cython. And so I need to write a new Cython file, and I call that in Kepler Cython v4. And as you can see, this is an incredibly thin wrapper of what I had, right? So I am using an external, just as I did with the math library, the pulling from math.h, I have my own header file. Oh, I guess I should show that, right? So you have to write a header file because that's how C understands interfaces. But the header file is just the syntax declaration of the method, right? So that's all that goes in here. So this 8.h file tells the rest of the universe what the C code, what the compiled C code is providing in the way of methods and their syntax declarations. So I am providing a single method, it returns an integer, it takes as inputs a double precision float, another double precision float, and a double precision pointer. So I pull from my own header file the syntax declaration, and I define it here. I am still using Cython functionality, so I import that, and then everything else is exactly the same. I have a Python declared method because I need this to talk to Python. So I can't use a cdef, I can only use a def. I type all of my inputs, and then internally I define the output as C double, and then I define my integer counter of number of iterations, and immediately set that equal to the call to the function, referencing the double that I just created, so that the information is passed back. And then I have my assert, which is a pure Python level thing, but it has no overhead unless you hit it. And that's it, right? So in order to compile this, I need a setup in this at this level. I could also have added this to my upper level setup, but I chose to build them all in place. So I'm just keeping them separate. So I have this other setup file. This one looks a tiny bit different because here, if I compare the two, if I can find the first one. So on the left is the setup file from the from the other directory where I had my individual 3 different versions. And on the right is the setup file for the version 4. And so the primary difference is here I'm Cythonizing just a list of methods. Here I am Cythonizing a setup tools extension, which packages together the Cython code and the C code. And the reason for doing it this way is because it takes care of the namespace, right? At runtime, the code, the executable blob has to be able to find the different pieces that go into it. And if I try to compile it this way, then ordinary Python is not able to parse the namespace properly. So I have to formulate this as a Python extension, packaged this way. So it's just a small caveat that you have to take care of. Everything else is exactly the same. So I go ahead and build. And actually, this was already pre-built, so everything's fine. I can take a look at the HTML that got generated, and there really shouldn't be any surprises in there. In fact, it looks exactly like the same as the HTML for version 3. It's complaining about the Python method declaration, it's complaining about the assert, and it's complaining about the return, all things that have to have Python interaction. Everything internal to here, 0 Python interaction. Right? Everything else is happening purely in the C blob, which is great, which is what I want. Okay, now I can do the timeout. Okay, then we wait a while, and it's exactly the same. And it's exactly the same because it literally is exactly the same. Mm-hmm. At that point, there is no difference between the pure C code that I've built wrapped in Python versus the fully optimized Cython code that I built wrapped in Python. They are one-to-one. Right? So I did my job with pure Cython really well, so I didn't actually have to do the C thing. Now, there are good reasons to go this route, though, and that is that it's way more portable across languages. I now have a C block that I can implement in a MATLAB Next file, which I'm not going to go through the procedure, but that's it. As soon as you have a piece of C that works, you can compile it within any one language, including Python and MATLAB and Julia and whatever the hell else you want. So that's a reason for going that route. You also, when you're doing more complicated things, and when you're getting into arrays, you get a lot more bang for your buck when dealing with pure C code. So just as an example for that, I'm very going to quickly show another worked example from another repository called Kepler Tools. And so in this case, this is actually exactly the same problem that we have been doing, except in the array input case. So literally the same thing, except here I am accepting an array of mean anomalies and an array of eccentricities. And I'm also allowing the user to set the tolerance and the number of iterations. And then this is the return, and this is just the size of the input arrays, because that's something that C needs to know. And so again, algorithmically, this looks exactly the same, except instead of having a single while loop, I am looping over all of the instances of the array. And so if I look at the Cython code that wraps this, it looks a little bit more complicated. And this is where all of the complexities of dealing with NumPy, with Cython, come into play. So you will see that I've imported NumPy. I've also done a C import of NumPy. And actually, this is bad style. I should have called this something else. I should have called this CNP, just to differentiate between the two, but for various reasons, it doesn't really matter. I am creating a Python D type that is just the np.double, and then I'm creating a C D type T, which is also related to the numpy.double. So I have to type things using the C data type, and then I have to ensure that the Python arrays that get generated are of the correct Python data type to make everything work out. I'm also toggling off all those various checks that I mentioned before. So we're not checking for writing to arrays beyond their bounds. We are not doing negative indexing, so we don't need that check. And we're not checking for none types in our floating point arrays. And so all of these things speed up execution. And then essentially the rest of it looks exactly the same as the example that I just showed you. I create an ND array, I type it appropriately, and I ensure that the np.zeros call gets the equivalent Python data type. If I skipped any of this, again, it wouldn't fail. It would just drop down into way more Python interactions, slowing everything down. And then I call the actual method. And I have to say that in this version, the last time I did extensive profiling of it, the gains are very marginal. For this particular problem, when you're operating over arrays and moving a lot, like the mildly Cythonized version does very well. And then really just using the C standard library math methods gets you most of the way there. And this just gives you like 5 to 10% gains beyond all that. But it gives you something. Okay, so that's Cythonization. And as we've seen, we can get pretty substantial performance gains, but you have to do quite a bit of work to get there. Now, if you're not willing to do that work, there's luckily other options. I guess before I go on, I just wanted to point out that in the Cython docs, there's a lot of really good tutorials. So there's a dedicated tutorial on calling C functions, which we just did. And there's a really extensive write-up on working with NumPy, because of course that's a major use case. And so a lot of the stuff that I just pointed out will be covered here. And then you can see also timing tests. And then there's really complex stuff on typed memory views and how to access arrays within the context of NumPy and outside the context of NumPy. And so there's a lot of complexity, and this gets really into the guts of Python and C, but it's kind of cool. Okay, let's say you have no time for any of that nonsense. You still have ways of extensively increasing the performance of your NumPy code, of your Python code. And I will point out 3 specific things. The first one is numba. So numba is, well, it tells you right here. It translates Python functions to optimize machine code at runtime, and then compiles them, essentially, right? And numba is very focused on scientific computing, and so it was really focused on the NumPy SciPy ecosystem of things. And the way that it works is you literally just add a decorator to your method. So I ran out of time, so I don't have profiling to show you on this, but this is something that you can easily play with on your own, because the overhead to this is very small, right? Now, in getting this installed properly is potentially non-trivial, but there's some really good guides. And it should be just some pip installs, really. It also allows for relatively straightforward parallelization. So if you have stuff that can benefit from easy parallelization, this is definitely a thing to try first before getting into the guts of more complicated parallelism. So that's one option. Another option is this thing called PyPy. And PyPy is a replacement for CPython. So CPython is the standard, is the reference implementation of the Python interpreter, right? Written itself in C. And so when you install Python, that's what you're installing. And when you run Python, that's what you're running. But Python is not an executable, Python is a language reference, right? And so there exist many other implementations, and PyPy is one of them. And so you can use it as a drop-in replacement for specific core language elements, right? The danger here is that it may not support all of the modules that you wish to use. And it may not support core features that are not part of these language sets. In particular, every single new thing that has been added in Python 3.11 and Python 3.12 won't be supported here. So that's the price you pay. But it is, and it also runs on only a subset of the CPU architectures that CPython runs on, but that's probably not a concern to the vast majority of people. But that's it, right? It's very fast. So if you can get away with it just by using a different Python interpreter, you can get much faster performance without making any modifications to your code whatsoever. The third thing that I wanted to point out is this thing called Cython, which is a performance optimizing just-in-time compiler for Python. And in theory, it is drop-in compatible with the CPython interpreter. So it's a full fork circa 3.8.12. So again, the full will not contain language features beyond 3.8, which you may or may not miss. And then there's light, which goes up to 3.10 and is pip installable, right? But of course, it is less impressive in terms of its speedups. The full offers theoretically 30% across the board faster benchmarks on a large range of things. So yeah, so all of these things can be used to create moderate speedups. Only Numba is likely to produce the kind of speedups that we just saw with Cython with minimal pain, right? So again, if you are trying to really speed up just like one core calculation, then my recommendation is to try Numba first, and then if that doesn't do it for you, then go the Cython route. And then, of course, this is only a subset of all the things that are out there. There's like 1,000 others. The 3 that I've picked out, in addition to Cython, are the ones that are the best established and the ones that have the most community support. So you're likely to find tutorials and templates and things for them. Okay, and that is Cython. So go use it or switch to a different language. Apparently, we should all be using Julia. So
I had a question.
yeah.
Is it easy to translate the setup.py? It seems like everyone wants to use the Py project TOMLs and then set up CFGs. Is that an easy translation?
Yes, it is. It fits completely under the CFG, and you can actually mix and match. You can still have the original extension elements. The reason why I use the setup.pys in this case is because I wasn't actually interested in creating a package. I just wanted to get the executables, right? So if you are just trying to get executables, then using setup.py is perfectly fine. If you want to deploy this as if you want to deploy Cython pieces as part of a larger project, then yes, you would go the Py project TOML and setup.cfg route. And yes, there's lots of tutorials out there of how to do the Cythonized parts of it, but it looks basically exactly the same. You just have a Cythonized call in there.